Okay, so we've established through rate laws the mathematical language that allows us to quantify how fast a reaction is going. So as part of this, we introduce the reaction rate constant and the reaction order. So it's the rate constant specifically which actually tells us how fast the reaction is going to go at some given concentration of our reactant. So it's within this rate constant that we term K that all of the kinetics are really wrapped up. So we're going to think now about what actually determines the value of K. What determines the value of K? And really there are two main things that determine the value of K. The first is the activation energy associated with a reaction. Activation energy. Now the activation energy, we give the symbol E subscript A, and this is a minimum energy that the reactants need to have when they collide in order for the reaction to happen. So the minimum energy of collision that will result in reaction. So what does that mean exactly? Well, we can envision what the activation energy actually is by considering what's happening to the overall energy of our reacting system as the reaction progresses. So we're going to draw now just a couple of axes. And on the x-axis, we're going to have something that indicates the progress of the reaction. And on the y-axis, we're going to have energy. So we're going to start with some reactants at some energy, and we're going to end up with some products at the end of the reaction. Now, what we have here is actually an exothermic reaction. The final energy is lower than the starting energy. But what actually happens in between here is what determines how fast the process will happen. So if we actually connect up these lines, we don't necessarily draw a straight line between them for how the energy varies throughout this reaction. Instead, what is much more typical is that there's actually an increase in energy before the energy then decreases down to the final ending point. And now it's this increase in energy, this barrier that the reaction has to get over, that is actually what defines our activation energy. The energy associated with the activation energy must come from the energy of the collision between our two molecules. So what that means is that as the temperature is increased, then the collisions become more energetic. And the reaction will actually go faster because there'll be more collisions that are actually able to get over this barrier. So collisions become more energetic, therefore faster reactions. So that is one element of what determines the value of K. It's how big this energy barrier is that our collision has to get over. And if we think back to kinetic and molecular theory, we showed that as a function of temperature, the fraction of molecules with high kinetic energy increases. So as we raise the temperature, the number of molecules that have high kinetic energy increased, and that's because we were shifting the average speed of our molecules to higher speeds. Higher speed means higher kinetic energy, so that means there'll be more molecules able to surpass this barrier. The other factor that determines the value of K, or how fast the reaction is going, is what's called the frequency factor. The frequency factor is a measure of how often collisions happen. But it also depends on the orientation of those collisions. So how often those collisions happen and some function of the orientation of the collision. The orientation is important because when we're breaking and making bonds, we have to orient the molecules in such a way that those molecules and those atoms can form these new bonds. If the molecules are facing in the wrong direction, these new bonds won't form and the reaction will not happen. So it's these two factors that give rise to the value of K, and there's a relationship called the Arrhenius equation that links these factors together. That is the Arrhenius equation. And the Arrhenius equation tells us that the rate constant K is equal to this factor A, so this is our frequency factor, multiplied by the exponential of minus the activation energy over RT. So you can see once again this factor of RT is cropping up in our expressions, and this is a measure of the average kinetic energy of our molecules. So we know as we raise the temperature, we're raising the average kinetic energy. What the Arrhenius equation is telling us is that the rate constant K is directly proportional to this frequency factor. So if we double the number of collisions, then we double the value of A and we double the reaction rate. And it's proportional to the exponential of the activation energy. So as we raise the activation energy by a factor of 2, for example, we'll actually slow the reaction rate constant by a much greater factor than 2, because this activation energy is present in the exponential. So this is an immensely important relationship, and we can use it to determine the activation energy of reactions if we were to measure K under different conditions, for example, and it can tell us something about the reaction mechanism in terms of how these molecules are actually coming together and colliding. So we mentioned that this frequency factor depends on how often collisions are happening. It also depends on the orientation of the collision. And it depends on the orientation of the collision because reactions involve these activated complexes. An activated complex is a reaction intermediate which is somewhere between the reactants and the products. So to get an understanding of what an activated complex is, we're going to consider an example of a bimolecular reaction, so a reaction between two molecules, and we're going to consider what happens with two different orientations of those molecules. And we'll see in one case we can actually form this activated complex and our reaction can happen, and in the other case we won't be able to form this activated complex and no reaction will happen. The reaction that we're going to consider is the reaction between ozone in the gas phase and NO in the gas phase. The products of this reaction would be oxygen gas and NO2. Now, just writing out the reaction equation doesn't really give us any indication of the geometry of how these molecules have to come together. So we need to know something about the shapes of these molecules. For ozone, this is a 3-atom molecule, and it has this kind of structure to it where we have 3 oxygen atoms. Is not linear, they're in more of a triangular configuration. Our NO is just a bimolecular, a diatomic molecule, and we can draw its nitrogen atom here and its oxygen atom here. We've drawn them here in this specific orientation because this is the orientation that will actually lead to a reaction. So these are going to come towards each other, they're going to collide with one another, and we're going to form the activated complex. Our activated complex for this particular reaction is going to be where we're beginning to break one of the oxygen bonds, but we then start to form an oxygen-nitrogen bond. So we have this configuration now where an OO bond is breaking, and an ON bond is forming. And this intermediate that we have here is our activated complex. This activated complex will then break down, and what we'll be left with are the products of our reaction, which, drawing with our atoms represented by balls, we have our oxygen and we have NO2. So in this example, the reaction only occurred because the molecules were coming together in such a way that this activated complex could be formed. And the probability that this would be the orientation of the collision is going to be something which is wrapped up in our frequency factor. So the fewer orientations of the molecules that will lead to a reaction, the smaller the value of A, the lower the frequency factor, and the slower the reaction will be. So if this reaction, or if these molecules were to come together in a different orientation, then we wouldn't actually see a reaction. So if, for example, we had our ozone molecule configured in the same way, and we had now our NO molecule approaching from the other side. So in this case, what we have is that the oxygen side is approaching first, and we don't get any reaction here. We don't have the ability to form this activated complex, and so there's actually no reaction here. So this reaction will only happen when our molecules are approaching in this very particular configuration. So this activated complex is really a transition state of the reaction. A transition state is a complex or a form that the atoms will arrange themselves in, which is somewhere between the reactants and the products. And the activated complex here is one example of a transition state. Now, a transition state is something that can't be isolated. We can't make 1 mole of a transition state, for example, and make any measurements on it. It's a transitory species that only exists during the reaction progress. Okay, so let's now return to this idea of being able to track the progress of the energy during a reaction, how the reaction is actually varying over time. So let's draw another couple of axes. Let's write our energy on our y-axis and the reaction progress on our x-axis. So we saw before an example of an exothermic reaction where our reactants and our products were at different heights. The products were at the lower level, and then we had some increase in the energy and then a decrease down to our products. So we have our reactants and our products. Now we're going down in energy here, which indicates that this is exothermic. But this initial increase in the energy, this represents our energy barrier. This is EA, our activation energy. And we have an activation energy even if the reaction is endothermic, even if our products are actually ending up in a higher energy state than our reactants. So let's draw another pair of axes. Again, we have energy on the y-axis and progress on the x-axis. So let's now start at a lower energy for our reactants and end with our products at higher energy. So now what we have is an endothermic process. And again, we don't join our reactants on products up with a straight line. Instead, the energy will track some kind of profile as the reaction progresses. In this case, we're going to draw something which looks, let's draw it in blue. Let's draw it something that looks like this. So the energy increases to a peak and then it drops down to our products. So in this case, we have this increase in energy over the course of the reaction, so it's endothermic. And here, the actual activation energy is the whole height of this barrier. So starting from our products, going all the way up to the height of our energy barrier. So in this case, we have a much larger reaction activation energy than we do in the exothermic case. And it's the height of this barrier which will determine in part the reaction rate constant. We can actually determine the value of this activation energy by rearranging our Arrhenius equation and then making some measurements in an appropriate way. So starting with the Arrhenius equation that we had previously, which told us that K was equal to A multiplied by the exponential of minus the activation energy over RT. We can take logarithms of both sides and actually get rid of this exponential. And when we do that, we can write down that ln of K is equal to minus the activation energy over RT plus ln of A. Now if we plot, having taken some measurements, the logarithm of the rate constant versus 1 over the temperature, then we'll get something which has a straight line that has a gradient of minus EA over R. So again, we can compare this to the straight line equation and identify that the gradient for plotting ln K versus 1 over T is going to be minus the activation energy over R, and then the intercept with the y-axis is going to give us the frequency factor. It's going to give us this value ln of A. So our experiment would then involve measuring the reaction rate at different temperatures and then plotting the natural logarithm of the rate constant from each of those temperatures as a function of 1 over temperature. Now, because we're plotting 1 over temperature, as we move to the left, we're actually increasing the temperature. And then the value of ln K is also increasing. So as we make those measurements, we'll get something that resembles a straight line, and we can then plot a straight line through that data in order to determine both the activation energy and the frequency factor. We can also rearrange this expression in such a way that looks very similar to something that we've dealt with before in this course, and that is the Clausius-Clapeyron equation. So we can, if we make measurements at two different temperatures, relate the rate constants at those two different temperatures. And we can actually derive an expression that looks very similar to the Clausius-Clapeyron equation, where we're taking the ratio or the logarithm of the ratio between the rating condition 1 and the rating condition 2, and that's actually equal to minus the activation energy over R multiplied by 1 over T2 minus 1 over T1. So this expression is extremely useful because it allows us to make just a couple of measurements at different temperatures and infer a lot of information about the system. Particularly if we know the activation energy, for example, then we can predict what the reaction rate will be at any other temperature based on just one other measurement. We're now going to work through a quick example where we apply some of this knowledge to determine the activation energy and the frequency factor for this reaction. The reaction that we're looking at is between the, it's for the decomposition of chlorine oxide, ClO, into chlorine and oxygen. And this is something that happens in the stratosphere of our atmosphere, and it's one of the reactions involved in the catalytic destruction of ozone. So what we're given from the question and what we could derive from an experiment is the rate constant K as a function of temperature. So T and K would be things that we would measure experimentally. In order to determine the activation energy and the frequency factor, we're going to be applying the Arrhenius equation, and that requires us to determine 1 over T and the natural logarithm of K, which helpfully are both tabulated in this table. So based off of the Arrhenius equation that we wrote down on the previous page, we can actually identify that when we plot ln of K versus 1 over T, then we're going to have a slope which is equal to minus the activation energy over the gas constant R, and we're going to have an intercept which is equal to the logarithm of our frequency factor. So the strategy to actually determine these values is graphical. We need to plot this data in a graph, determine what the slope and the intercept are. So we would plot the data and fit a straight line. The data will look something along the lines of this, where we have ln K on the y-axis, 1 over T on the x-axis, and we have data that falls nicely on a straight line. Using any graphical software or a graphing calculator, we can plug these real numbers in and determine what the gradient is. And we find that the gradient is equal to minus 1590 Kelvin. Remember that when we find a gradient, we're taking delta y, or the change in y, over the change in x. So we have 1 over T in our denominator, so that brings the units of temperature, the Kelvin, into the numerator of the value of our gradient. The intercept has a value of 28.0, and the intercept is just the value on the y-axis when we intercept with x equals 0. So in this case, the logarithm of k has no units associated with it, and so the intercept itself also does not have any units associated with it. So now we can determine our activation energy and our frequency factor. Let's start with our frequency factor. We have ln of A is equal to 28, and so very straightforward, we can determine that A therefore must be equal to 1.4 times 10 to the 12. Now we can determine the activation energy by rearranging this expression. So when we rearrange it, we can write down that the activation energy is going to be equal to the slope minus 1590 multiplied by the gas constant 8.3145, and that's it. We have only needing to take the minus over, which we've done here, and we can determine the value of our activation energy to be 1.32 times 10 to the 4 joules per mole, which we would usually represent in kilojoules per mole, so 13.2 kilojoules per mole. So the barrier of this reaction is actually not very high, and so this reaction actually occurs quite rapidly. We know this isn't very high because this is actually very close, or very much lower than the average kind of kinetic energy of a gas, which is given by 3/2 multiplied by RT, which numerically is a number which is quite a bit bigger than this. So using our Arrhenius equation, or the Arrhenius relationship, we've shown how we can actually determine the values of our activation energy and the frequency factor for a reaction based on knowing the temperature and the rate constant dependence on that temperature.